RF, or radio frequency engineering, underpins a huge amount of modern life. One of the most familiar applications of RF is in radar, which uses radio waves to detect objects, determine how far away they are, and even how fast they're moving. Radar is used in everything from marine applications to consumer devices to meteorology. But RF has a bit of a reputation as black magic. That is to say, despite its common use in electronic devices, RF engineering as a discipline is notoriously difficult to grasp. Here to help us understand the basics and cutting edge of radar technologies, and to navigate the black magic wilds of RF, is Greg Clark, Senior Manager of Defense and Aerospace Markets at Qorvo. Greg, welcome to Tech Chat, sponsored by Mauser Electronics.
Happy to be here. Glad to join.
Today we're going to be talking about radar, RF components, and SWaP-C. We've got a lot to pack in to this time, but let's make sure that everyone listening has that context first. Can you super quickly define SWaP-C so everyone's on the same page?
Yeah, size, weight, power, and cost is what the SWaP-C stands for. Size of the radar, weight of the radar, power of the radar, and then probably the most important one for the business guys is the cost.
Right. And we'll be getting into all of those concepts as we go along, and we'll also be talking about which sort of economy of scale we're dealing with, right? Because as everyone's sort of aware, we'll dig into the differences that are basically in place when you're talking about specifically defense and aerospace markets. Is that right, Craig?
Yeah, it's kind of maybe not so much specifically defense and aerospace, but what radars get used for. They're actually kind of all over the world, and probably part of everybody's lives, and they just don't realize it. So, but I will focus more on the defense and aerospace side.
Awesome.
I will highlight a little bit where people in sports use a radar, people driving their car use a radar. Just as there is commercial aspects to it.
Perfect. Yeah, and I expect that people are going to learn some stuff about where radar is in their lives and they didn't realize.
So this is what I want to talk about. From an agenda standpoint, very high level, just a very quick market overview in terms of dollars spent related to radar. There's a slight radar introduction. So for those that may not know what a radar is, types and applications, then we'll have some basic equations. And then where I really want to focus is probably in the SWaP-C, the trade-offs where RF power versus packaging, reconfigurable technologies that are emerging today, heterogeneous packaging and advanced packaging.
Yeah, a lot of actionable things towards the end here. No spoilers, but I think I'm really excited to also dig into some of these. Here is a spoiler. There's lots of math. Very excited. So, okay, what can you tell us about where radar's positioned in the market right now?
Well, right now today it's about $16 billion. That was actually in 2020 as far as the global spend on defense radars. You can see in the chart there in the upper right corner from Strategy Analytics, it continues to grow. Obviously, you have to believe the strategists. My experience tells me that it continues to grow. I've been in this industry since 1995, and it always has this steady, stable growth rate. Some of that is, it's driven by legacy support. We got to keep supporting what's out there. Radars are built to last, especially in the defense and aerospace market. So we got to keep those updated, keep those operating. But then we have to upgrade them too. And that's when you start seeing things like the ESAs that are becoming more popular as technologies advance today. We also have our array types. So the traditional reflector arrays, which again we'll talk about shortly, versus the phased arrays or the fixed arrays.
Right.
Now we got another thing that drives the radar market is the components that go into there. I'm going to focus we'll strictly focus on the RF. It won't. I don't talk about the microprocessors or the algorithms, but the RF side. So where the gallium nitride, gallium arsenide, and silicon-based RF components exist. And actually, I'll probably focus even more on the PA and the LNA transmit receive side.
I'm assuming something here, but have you heard RF referred to as black magic before?
Oh, absolutely. In fact, my first, just a side story, my first training class in my first job at Texas Instruments, I went to the Engineers 101 class that they had. And we got to talk about everything. And then we had one slide on the RF, and all it said on it was black magic. So that was
Fantastic.
my entire RF training with my first job. Fortunately, I'd had some training prior to that, but it was a
Need to know basis, huh?
needless to say, I left a little bit disappointed. So.
Oh gosh. Yeah, I can only imagine. And I think that's, honestly one of the reasons that people will be tuning in to hear you talk about this is because it does still seem to be black magic across the board, and any glimpse behind the curtain seems very welcome.
Yeah. And, RF is all based on equations. Once you get through the math, then it becomes just like any other engineering discipline as far as I'm concerned.
I'm literally writing that down right now. If you can get through the math. That's comforting, I think, for some people in our audience. I feel as though LiDAR gets a ton of the limelight right now. It's kind of like almost like a Marsha thing going on right now. Do you feel that radar is underserved in terms of conversation, or do you see it as being something that's complementary to LiDAR?
I think it's quite complementary. I'm not overly familiar with LiDAR. I know it's a buzzword, or it can be a buzzword out there. I think it kind of depends on the people you talk to. I know from my industry and in my role, I don't talk about LiDAR at all. Sonar on a very small degree. Radar is what we talk about. So from a market's perspective, I think it kind of depends on who you're talking to, really.
Okay.
Radar, but they're all complementary of each other. But radar is still very much a strong system solution and market space.
Awesome. And yeah, we'll talk about all those different applications for radar in just a few minutes here.
So it's radar detection and ranging. I'll just simply read it because it's the best way to describe it. Uses the transmission and reception of electromagnetic waves to detect a reflective target at some distance. I mean, that's really what it is. You see here in this image, the kind of the block diagram shows the airplane as the target. It says target cross section there, but it's just the target. The radar has the antenna. Again, that could be reflector. There's multiple ways to define the antenna. Then it has in this case, it's showing a circulator, but some of them have a switch. But then you have the transmit side, which is actually sending the signal out. And then you have the receive side, which is receiving the reflected signal back. And then behind that receiver is, to me, probably where more of the black magic occurs. But because I don't really get into signal processors or how they interpret that or how they interpret the signal back through their algorithms. So software is not my strong point, so I tend to avoid it where I can.
You're in good company. Right. And just to reiterate, same sort of general concept. The DAR part is the same. The difference with LiDAR is light detection and ranging, and sonar is sound detection and ranging, right?
Yep.
So everyone's...
Sonar is sound, radar is RF, and LiDAR is light. All
right. So these are terms that people in our audience may be familiar with. They've probably come across them in the past, but can you give us a breakdown of reflector versus phased array?
Absolutely. So reflector is more of the historical, traditional, what most people would probably imagine what a radar looks like. It's the dish that you see at the airport that's spinning around. In fact, that image of the red and white one there is probably an air traffic control radar at some airport somewhere. Again, traditional, historical, very applicable in the markets today, still being developed and used. But then you have the phased array, and that's what's on the right-hand side of the chart here, where it's basically a flat face, and you have multiple faces. So it can be a single array face, kind of like what you see right there in the middle, kind of the gold-shaped. That's probably out of the nose of an aircraft, if I had to guess. Or you can have, something like what you see in the upper, on the right-hand side, at the upper, very large low-frequency arrays that are multi-faced. So they're pointing in multiple different directions. But the phased array is kind of the new thing. So
you can absolutely tell the difference just at a glance, like physically. They look different, and just to be, to put it in those flat terms, it seems as though that reflector design is meant to sort of scoop up signals, and the phased array is perhaps more like, for lack of a better analogy, sort of like a mesh network where it has a lot of smaller receptors that can pick up signals simultaneously.
That's exactly it.
Awesome.
That's a great way to describe it. The reflector scoops up the signals as it finds them, or it broadcasts out the signals that are coming off the transmitter.
This radar classification that we're seeing here, is this specific to phased array, or is this reflector and phased array?
This could be both reflector and phased array, but I'm going to, for the rest of the talk, it's really going to be more focused on the phased array or the passive arrays. But they can still be applied here. So you have, and classification may not be the best terminology here because you can classify it as, ground-based, so it sits on the land somewhere, terrestrial. Shipborne, exactly what that means, sits on a boat somewhere. Airborne and spaceborne, those get lumped together because they're, not terrestrial or ship-based. Each of those classifications can have their own set of requirements from a reliability and function standpoint. The ground-based, as I said earlier, these are terrestrial applications, so we can jump down a little bit. I think just on the space and airborne, my opinion is these tend to have the harshest of requirements. Some might argue that the naval or the shipborne has very harsh requirements because of the things like salt fog, and you're also looking out over the water, which can have lots of interference issues. But I think the airborne and the space, from a reliability standpoint, tend to have the toughest requirements because of the temperature variations that they have to go through. And if you think about it on the space side, it's, one, it has to launch, and that's a harsh environment by itself. Most launch locations are in pretty harsh environments, if you think about where they launch rockets from these days.
Right.
And then you get into space, and, it's a vacuum. It gets the extremes of, it gets the temperature extremes, whether it's in the sunlight or in the dark side of the Earth. So.
Yeah, hard to think of a more extreme environment than that, really.
Oh yeah, I mean, I've heard people say, oh, it's in a vacuum. How harsh can it be? Well, it can be really harsh.
Very much.
Given the fact that minuscule particles, are floating around up there, moving at very high velocity.
No air resistance. They're little projectiles,
Correct.
right?
That's right. Little bitty missiles flying everywhere.
Little bitty missiles.
And then away from physical location of the radar, the other classifications from a system perspective, you get continuous wave radars, that they're always on, they're always transmitting, and then there's an antenna or multiple receiver antennas passively collecting the data. And then you get to pulse radars where they're sending out a pulse, and then it switches to receive and waits to hear back what that signal is.
Right.
So here it's, I wanted to just kind of highlight where radars get used today. I know when I think of a radar, I go strictly to defense and aerospace, but maybe that's just because of my experience, or the weather. Everybody gets to hear their weatherman talk about the Doppler radar. But we have long range radars. These are called over the horizon type radars. They're looking way off in the distance to see what's coming at us. Back in the Cold War, probably even now, they're still used for watching for intercontinental ballistic radar missiles. So long range detection. You have maritime radars, which we've talked about on just a little bit. These are what you see on the boats, whether it's the naval defense ships or whether it's a commercial radar. And those can range from, searching for enemy targets to targeting, the enemy, or they could just simply be monitoring the weather to ensure that those ships don't end up in a bad spot. You have automotive radars. I think everybody's becoming more and more familiar with these. Automotive radar has been around now, at least 10 years that I can think of. Very high frequency, very short range. These are proximity type systems. They're warning you that there's a car next to you or that there's an object so you can avoid hitting it. Low power, short range. You got space object tracking. This is becoming more and more important as we continue to launch more and more satellites up there. not to mention all the space junk that exists there today. You know, old rockets, things like that. But people have got to start monitoring what's up there. And again, the importance becomes critical because the way things are going today, we're about to have a whole bunch of satellites up there for communications.
Mm-hmm. And some of them are actually quite small and might not be as easy to track.
That's right.
In the vacuum of space.
The CubeSats, these things are, the size. So you have satellites that, size of a bus. You have satellites that are the size of, a laptop in, area but square or a cube shape. So, and then you got this, as I just mentioned, the Doppler weather radars. This is what everybody's used to seeing, when they watch the weather, as it scans around and shows you where the clouds are. Aviation radars, again, in front of a nose of an aircraft here. I don't recognize that aircraft, but the nose cone is basically where the radar is. It's looking out into the distance to see what's coming at that aircraft. And then you get to the things that people don't really think about. The consumer. One of the popular items right now with radar is the ball tracking and swing for a golf player. Another one is the radar detector that people have in their cars. And then finally, industrial. Again, this kind of similar to the automotive, but these are proximity sensors, home security, things like that, or industrial to ensure that, something doesn't run into something else in the factory warehouse.
Or automated mine carts, that sort of thing, that are running about autonomously and need eyes and ears, so to speak.
That's another good example, the autonomous vehicles, where radar becomes a critical function so that they don't run into themselves or something else.
And you kind of alluded to this early on when you were talking about the Doppler and weather tracking. But can we talk a little bit about basically, you call that S-band, right?
Yeah.
Can we talk a little bit about all of the different bands that are applicable here when we're talking about radar?
So radars go, from megahertz range, 3 to 30 megahertz high frequency, which is what HF stands for, all the way to 300 gigahertz. Automotive radar right now is, 77 gigahertz, and everything in between. You have the low frequency stuff, and I'll call low frequency S-band and below, so 4 gigahertz and below. So the very low frequencies, again, over the horizon, long range radars. Sorry for my misspelled word there.
Sorry.
The VHF, again, very long range, surveillance. These are the things that are just out there looking and seeing what they see, and then reporting. The receivers are reporting back, hey, we see this target. L-band, again, long range surveillance radars. You see these mostly in ground and ship applications, so shipborne and terrestrial. S-band, now S-band and C-band, you kind of get into the moderate ranges. S-band works really well for weather because it picks up the moisture in the air, so you can see the clouds. And you can see great advancements. They're going so far as being able to track, whether there's hail. They're starting to learn how about the signatures of tornadoes in the actual radar signature. I know they talk about the hook, meaning that tornadoes can be potentially nearby. So that's what C-band are, but they're also used for military applications, tracking, kind of just searching what's out there. And then you get into the higher frequencies. X-band is kind of a traditional higher frequency. I'll put that in air quotes because it doesn't seem to be high frequency anymore. But this is short range tracking, high resolution. They're looking for, target detection so that they can, keep it in their sights so they don't lose it. But you see a lot of X-band on, aircraft. You'll see them on the shipborne as well. And then KU, K, and KA band. I don't see a lot of KU band these days, although I think it's picking up. It gets operated similar to X band. The K and the KA band stuff, it's high resolution mapping. They do have their downsides in the sense that they suffer from the weather and atmospheric attenuation. But police traffic radar is a good example of a commercial or semi-commercial for KA band. What you do see Ka band being used for is a lot in missile systems. Because if you think about it, they're short life, and really what they're trying to do is maintain their position relative to the terrain that they're flying over before they get to their target.
All right. So if you're comfortable with it, we can kind of move on to the math portion of our program.
Yes. There are books out there that will give you a much broader overview of radar equations and radar, how to determine what a radar needs to do, or how to calculate the fundamentals of the radar. But I wanted to provide some overview here. So, some of the basic equations, you have your radar range. It's the speed of light times the change in time divided by 2, because you have a signal going out and a signal coming back. You have the Doppler shift. This is, when you hit the target, that target results in a change in the target and the velocity of the target, v, in this particular equation, results in a frequency shift. So a positive or a negative. Positive means it's coming towards you. A negative means it's moving away from you. But that's what FD, or Doppler shift, is. You have pulse repetition frequency. This is, actually we'll talk about this more in depth, but basically this is the number of pulses, repeated in a signal in a specific time. It's the inverse of the pulse repetition interval. These are basic radar terms that radar system engineers will talk to you about. Average power. So you have peak power, which is, in this particular equation, is P sub T. But average power is the duty cycle, so DC times that peak power. You can derive it such that it's the peak power times the PRF times the pulse width, so which is tau in this occasion. So, and then you have bandwidth, which is 1 over tau, or 1 over the pulse width. But again, very basic. So signal detection, this is, it's really the probability of detection and the probability of false alarm. This is what defines or describes the general performance of the radar. It translates to a signal to noise ratio. Here, we've got a very simple, PD versus PFA to provide a signal to noise ratio chart. There are multiple versions of this, but the signal to noise ratio, it leads to the definition of the transmit power, and as well as the RF noise figure, and then finally the gain of the system. Here we're talking about range and resolution, and really the important thing here, not really focusing on the equations themselves, but it's range and resolution that conflict with each other, in the sense that, generally speaking, long range means low resolution, and vice versa. So if you want long range, you have to have a low PRF, is another point here. The higher resolution, which in the lower right-hand chart of resolution means a lower number on the y-axis, results in a low pulse width. And if you have a low pulse width and a long range, you can result in a high peak power, which becomes a challenge, because now you're trying to figure out how you generate that much power in order to get both range and resolution resolved. So there are lots of equations here on this chart, but really the most important one is the very bottom one, which is the receiver power for the radar. I won't go into the specific derivations of this, but receive power is basically your peak power, your antenna gain times the radar cross section to get to that receive power. And receive power is basically how much signal you can achieve, or how much signal you can receive at the time when the signal comes back. Array pattern. So this is basically talking about the phased arrays. So in this case, the focus is on the images, not the equations so much. The equations kind of describe the math behind what the pictures show. But in the upper right corner, you see a single patch antenna that has an isotropic pattern, which is the red bubble to the side of it. If you take that patch antenna and populate it in a 2x4 array, the bubble changes in the sense that it becomes more little bit taller, squeezes together so it narrows it down. But then you also get these side lobes that are seen on either side of it in this image on the lower right side. You don't have a picture of it here, but let's imagine you took that and made it a 4x4 array. You're going to see the middle red portion get smaller again, probably a little bit higher in power or higher in as far as its energy level. But you're also going to see two more side lobes crop up so that the middle red is surrounded by four of those little side lobes. Probably a little bit hard to imagine, but the array pattern defines what your beam looks like as well as its side lobes. And these equations here are the basics of how to define that. And then we jump to the next slide, which is the beam steering. So prior slide just showed it shooting straight up in the air or one direction. Here, if you change the phase of each of your elements inside the phased array, now you can start steering the beam. So you can start directing the energy to a certain location, both transmit and receive. You have to worry about grading lobes, which is as you scan too far over, you'll get a lobe coming up on the other side. In the upper right, you can kind of start seeing that with you have the red main lobe, but then you can see the three grading lobes starting to come up. You have to watch out for that because a grading lobe leads to errors in your radar. So I'd say most phased arrays define their array spacing at half the wavelength between elements of the highest operating frequency to avoid those types of grading lobes and those types of errors.
Right.
And then really quick on polarization, there's the linear polarization means it's one direction electric field. Circular polarization means you have both a vertical and a horizontal signals going out. Really, this is not so much the RF hardware. This is the antenna that provides this. But circular polarization, it adds complexity to that system. It helps reduce the impact of interference and increases the robustness of the radar to detect of the radar's ability to detect that target. But it comes with, again, more complexity with the algorithms on how to interpret that data. It can also result in increased number of components in order to be able to support it. And now we get into swap C, and what's enabling some of the swap C discussions. If I kept the number of elements, looking at the red number of elements, and then the spacing nx and y, if you keep them the same, this just kind of gives you an overview of what's the art of the possible, at least from my system engineer's point of view. The point here is low frequencies, L, S band, let's say, in this particular chart, your lambda over 2 is pretty large relative to the RF components. So you have lots of space to work with. That gives you the opportunity to use different types of components, different type of matching, as well as it gives you lots of space for thermals to get all your heat out, because these radars generate heat because they're not 100% efficient. That would be a cool thing if we had a 100% efficient radar.
We'll wait for it, shall we?
Yeah, I don't think it'll never happen in my lifetime, or my children's lifetime. But and then you get up into the X and the Ka band. Just looking at the second row there, you can see your lambda over 2, which is your array spacing, getting much smaller. But you're still trying to fit components within those array spacings in order to generate the power that you need. So that limits your power levels. It limits your ability to pull the heat out. And this is where we start getting into the swap C type discussions.
Right. And just very quickly, this chart seems very handy. Is this a good representation of the sort of a glimpse into the mind of one of these engineers who's asked to design a radar system?
I think it is. This came straight from one of my radar engineers, system engineers here at Qorvo. It's an incomplete chart, as you can see, because we don't have the KU and the K bands calculated yet. But yeah, I think it's a fair representation. I think it's a fair representation in the terms of, what are your trade-offs and what the frequency band can do relative to your power as well as your capability. So, one of the things that pointed out here is looking down below at the near the bottom, RFFE integration. This is RF front end integration. At L and S band, he says it's not required. That's probably true in most cases. At X band, he's saying it's required. And when we talk about integration, we're talking about integration of functionality. The PA and the receiver, or the PA on the transmit side and the LNA on the receive side, in the same package, so that they take up as little possible space as possible. Because again, your lambda over 2 spacing is very small.
Yeah, that's swap C thing, right?
It's swap C, so that becomes the power versus the size type comparison, and cost rolls in there too. Again, the business guys won't let you get away from the cost.
Of course not.
Speaking as the business guy, so I understand.
Got to actually build the thing, right?
Yep, absolutely true.
Right, so this is a pretty straight up breakdown, huh?
Yeah. So we talked about size, weight, power, and cost. That's swap C. Size, it's the integration, it's the packaging, it's the volume of the physical size of the radar or the system. It's also the BOM count. The more components you have in there, the more space you have to worry about. Weight, it's thought about in multiple different directions. So you got to worry how you're going to get it there. Is it going to fit on the back of a semi? Is it going to go on a ship? Does it physically fit in the location that you want it to fit? The payload, especially in the spaceborne or the airborne type systems, launch, flight time, and then fuel burn is an interesting one because it's fuel not only on how you get it there, but let's say your radar is in a remote location. It's got to operate off something. Something has to power it. So I've seen radar engineers calculate down to the gallons of fuel, diesel or gasoline, that they'll have to use to keep a radar operational for a certain number of hours of the day.
Wow.
To keep their generators up and running. And then you have power. So this is your performance, your RF power. It affects your resolution, your range, but then you also have to worry about the heat that power generates. And then finally cost, and how that kind of rolls all these together. How much does everything cost to build it, individual components, to manufacturing the whole system, to operating it, to service life? How do you maintain this thing?
Right.
Okay.
Trade-offs.
That's right. So now we're going into enabling technologies that affect the swap C. There's industry-leading semiconductor technologies. So you have your gallium arsenide, your gallium nitride. Both are used in the transmit. GaN is gaining ground, continues to take ground in the transmit side because of its power density capability. The BAW and TC SAW, these are more back-end filtering technologies to filter the signals out before they go into the A to Ds and the D to As. But and then you have SOI, silicon on insulator, SiGe, silicon germanium, and then CMOS. These are all back-end, control capabilities. SiGe, SOI, actually for low power, like automotive radar, work really well because you don't need a lot of power. You just need to be able to see something kind of nearby. And then you couple that. So those are the semiconductor technologies. You couple that with packaging, world-class packaging. That's not necessarily specific to Qorvo, but I like to think we're world-class. But QFNs, so quad flat, no lead packages. This is, a plastic overmold package. You have air cavity surface mount packages for performance at the higher frequencies. Flange packages. This means they have a slug of metal connected to the base. And then you couple that with integration. Now you're taking the semiconductor technologies and the packaging, and you're putting them all in the same package. You're mixing the technologies together to create modules, and that leads to swap C type, decision-making processes.
Mm-hmm.
Okay.
And it's funny, I've wide bandgap semiconductors like GaN and gallium arsenide, all of those. I think generally in the market, people associate them with specifically power applications. But what I'm getting from this conversation with you is that radar and RF applications in general are actually much more interesting in terms of wide bandgap than perhaps people know off the top of their head. Is that right?
Yeah, I'd say so. There's more applications for the GaAs and GaN. mean, the GaN's going to be your PA and maybe its driver, but the gallium arsenide, it's going to be everywhere. The SIGI or the SOI and CMOS are definitely have their benefits that could replace the gas, but for my opinion, again, sheer performance, gallium arsenide and GaN are going to be your 1 and 2. So.
Well, and this is hopefully a nice segue into this next little section here. What's one of the most promising wide bandgap semiconductors that you guys are pursuing at Qorvo?
The GaN on silicon carbide. This is what is primarily in our portfolio for our PAs today, and where we spend a great deal of effort improving upon. So it's your highest RF power for the transmit side, for the size across the frequency spectrum. And I would say that is UHF all the way through right now Q and V band, which are, up in the 50 gigahertz range. And it has operates reliably at high junction temperatures. So 10 to the 7th hours MTTF with a channel temperature of 225 degrees C. And then I've already mentioned the frequency range. We have operational capability in our designs from 500 megahertz through 100 gigahertz. And Perfect. Then you add that to the silicon carbide, which is the substrate that the GaN epitaxial layer is grown on. Excellent heat transfer. It's one of the best heat transfers that are out there, except maybe diamond.
Yeah, and you've mentioned that thermal element several times throughout. It's actually very illuminating how important that is in these systems.
It is. The thermal side of it is, so if you can produce that much RF power, you're not going to get 100% transfer of your DC power into your RF power. There is some amount of efficiency. And that translates to how much heat is going to be dissipated by that in that structure or in that design. Packaging and RF power, we have discrete, and this is not just Qorvo. I highlight Qorvo because that's who I work for, but discrete packages, we have integrated FETs that have matching around them called the IM FETs. We have MMIC solutions, and then we have MMIC solutions in different types of packages. But from a packaging standpoint, you have flanged packages. So the top 3 here in this graphic are flanged packages where you have the metal structure the device attaches to, and you have a lid that goes over the top of it. They're typically larger in size and weight, tend to require hand assembly versus an automated system. Because they can handle the thermals better because they have more heat spread because of that metal structure underneath them. They can handle higher duty cycles, even up to continuous wave type operation. They tend to be single gain stages for the FETs. Multi-stage MMICs, for that 1/3 from the top where it says MMIC around 3055 is the part number there. The IM FET, which is the one just above that, it needs a driver stage because it's a single stage amplifier typically, although I'm seeing multi-stage IM FETs. And the IM FET, it's heterogeneous in the sense that you have your GaN transistor, but everything else around it is off-the-shelf components or board material or ceramics that create the matching to create the performance. And then you go into another type of packaging, which is the QFN. This is the plastic overmold. So you take the MMIC or the FET even, you attach it to a lead frame, which is typically copper. And then once you get all the wire bonding done, then you put it into what's called the overmold machine, and it literally just basically runs melted plastic across the top of it, and then you singulate that. Where these help, it's size and weight. These will be your lightest and your smallest capable. They will enable automated assembly because these things can show up in tape and reels, and they just stack them on their automated assemblers. Thermally, they're not going to be as good. They're going to have a lower duty cycle typically, although there's some advancements going on there that don't really want to get into here, but there are advancements there that are helping that.
Your next tech chat, perhaps.
Yeah, maybe. Yes. And from a system standpoint, in order to get the gain up, you're distributing your gain. So you maybe need a smaller driver amp versus a larger high gain amplifier to drive the FETs. But the other thing that shows here from a slide perspective is, 1.8 kilowatts. That's low frequency. Where the very bottom one, that's actually an S-band part. It's capable of 100 watts, 150 watts, is what we're driving towards. Moving up to X-band, you're seeing 100-watt capability. And that's not just from Qorvo. That's, my competitors out there. They're doing the same thing.
And just as a footnote here for people who might be wildly Googling right now, IMFET is the internally matched field effect transistor, and MMIC is monolithic microwave integrated circuit, right?
Yeah. IMFETs are going to require your biasing circuitry outside of the chip, whereas the MMIC takes care of almost all that internally. You'll have to do some off-chip components for matching. Data sheets from any vendor will provide the level of detail you need there.
And you're introducing a new concept here that might be new in a shift in the market. And let's just see what you say on this one, the reconfigurable technology.
Yep. So reconfigurable technology's probably been around for a long time. I know back when I was a designer, I spent time working on reconfigurable applications. But in this case, it's reconfigurable in the sense that we're providing a capability to create a radar system, or providing a component that will allow you to create a radar system that is both X and X band functionally capable. Now, there's some work that has to be done on other components, but from a PA perspective, and an LNA perspective for that matter, that's in work, is this S band, X band capable system. So you have a single antenna, single component that does both S and X versus having one of each. Traditionally, you have one of each. You have an S-band radar system and you have an X-band radar system. Now we're giving the opportunity for the system integrators and the system design, or the people that need it, to have both all in one, wrapped up in one system. The idea here is, again, more about integration and BOM count reduction. So the block diagram here is just a basic RF chain that you would see in a radar. You're going to have, going from left to right, you'll have the attenuator, a phase shifter, so that's your amplitude and phase control. You'll have a low power TR switch that then tells you, well, I'm in transmit mode or receive mode. You're going to have a driver amplifier on the transmit side and a PA. And then on the bottom half of the block diagram, you're going to have an LNA and the limiter. The limiter is actually to protect the LNA from either jamming signals or just a high power signal. And then you'll have, the component before the antenna, the high power TR switch or a circulator function. And then you have the antenna. Where Qorvo and other manufacturers are kind of segmenting out these components and combining them into what makes sense. One of those paths is the larger green polygon and the larger blue polygon. The core module is what I call it. There's probably people call it differently. Controller module, whatever. And then you have the front end module. The front end module, you're integrating the PA, the LNA, and the limiter and the high power switch into one component, whether that is all monolithic as one MMIC, or if it's heterogeneous, meaning you're using GaN and GaAs combined to get the functionality, is kind of up to the application. As well as the volume need. And then you have the core module. These are, they could be SiGe based, they could be SOI based, it could be a combination of gas and silicon, but it's combining what I would say are the non-GaN high performance and low noise figure performance needs that you see in the front end module into a core chip that allows you to, again, it goes back to the integration. Instead of having, 4, 5, 8 components to 2, that as the system user, you're buying 2 versus 8.
Wow, that is actually pretty big jump there, isn't it?
Yeah, and that's the next slide is an example of just that for the front end module. I would have examples of the core module as well. Here we're taking 4 existing products in the Qorvo portfolio, which if you add up all the sizes there, you can kind of get an idea of how much area they take up into a single 7x5 millimeter multifunction TR module. So it's a front end module. You get the best of both worlds. You get the benefit of the gas on the receive side, you get the benefit of GaN on the power side in a small size. So there's your size and weight advantages. You're getting the power advantage because you're using GaN. Cost, ideally, it should be a lower cost solution. Even if it's a higher priced solution at the component level, it should be a lower cost solution at the system level. Because again, you're not having to source 4 pieces, you're having to source 1 piece.
Right.
And that should result in cost reductions. Dramatic reduction in size, simplifies the customer system, maximizes RF performance. So you have further integration for the size, weight, and cost improvement. So now we're looking at, well, do we integrate more? Do we not just do the front end module? Do we pull more of it together? And that's what this graphic kind of shows is you have 4 front end modules with this kind of unnamed gray box in the middle. Well, that would be your core chip, but it's a multi-channel core chip. So you're integrating all that together into a single circuit. This is not a new concept. It's a concept that's been around for many, many years. It's just, I think now the manufacturing technology and then the technology of the components themselves are allowing us to be able to do that. So think about it more. You get more SMT assembly with fewer components and interconnects. So you don't have to worry about quite as many solder joints. You don't have to worry about, board space or, things like that. You get a smaller board, so you maybe avoid a little bit of a warping issue. You get fewer connectors and cable assemblies. You don't have, I don't know if you've ever seen a radar board, but they're fairly complex. Well, they're really complex. Let's say that. And one trace mistake can create a whole bunch of problems, and you're redoing that array or respinning that board, or you're putting in a little jumper wire. So, and then we start talking about vertically integrated electronics, and that's where we start talking about advanced RF packaging. I will say some of this packaging capability already exists today, and I would say our commercial low frequency mobile brethren are already using it. But we want to apply it, at least I want to apply it to, I'll say radar, comms, anything high frequency and high power, but focused on radar right now today. But we want to go from multi-die chip and wire, like I showed a few slides ago, where you have these SMT packages, to vertically integrating this stuff. So now you have the multiple power amplifiers. I don't show it here, but there would be an LNA in here as well. So for the receive side. And then you have the beamformer or the core chip, the multi-channel core chip that controls each of those power amplifiers and front-end modules. You attach that to a interposing laminate base that's very complex as far as the number of layers, that then it's got a ball grid array that then attaches directly to the antenna board. The PA, the LNA, the beamformers as needed, they're flip chip, if we need to be able to pull that heat out. And then that goes to an exposed heat spreader that then goes to the housing. You have this thermal interface material. This is actually, to me, one of the most challenging parts of this entire concept is the thermal interface material. It's got to be something. And what it is I think what needs to be better defined, because you're trying to pull out substantial amount of heat in a very small space. So if you imagine this has low thermal conductivity, then you're just like putting an insulator between your PA and your heat sink, which is the housing fixture. But if it has high thermal conductivity, it just acts as a pass-through. So it's kind of like pinching off a water hose. That's one way to look at it.
And this is sort of issuing a challenge to maybe some of those material science engineers out there who can help us with this thermal interface.
I know they're working on it today, and I'm sure we'll come up with solutions.
the more interesting that this sort of space becomes with RF packaging, which is obviously, it's not going to go away. The demand is going to increase and increase. And especially as you get into those higher frequencies and higher bandwidths for especially telecom, the more interest there is in research in this space, right? So we should sort of expect to see more volume and also more investment, right?
Well, that's right. And that's kind of the Qorvo model, I guess is the best way to describe it, is we want to exercise our commercial engagements to drive up the volume so that we can put money into the research and development for this type of capability, so we can drive, capabilities across all the market spaces. It becomes the cycle of life. The research dollars get spent by, the defense and aerospace guys to try and do something like this. That gets commercialized, and then it just keeps cycling through itself.
Mm-hmm.
But this is the future, I think, to get to higher and higher levels of integration. Maybe not this final, pictorial, but
mm-hmm.
this is where I think the technology is going.
Core concepts, yeah.
And who knows? Maybe there'll be another epiphany like gallium nitride. Maybe we'll see another technology that takes over. Back in the 90s, gallium nitride was just kind of a researcher's pet project.
Yep.
Now it's proliferating across the world.
It's been a long time coming, but I like that. Greg Clark issues challenged. The next big thing, we'll be waiting for that.
I'd love to see it. I hope I'm around to be able to see that.
I know, me too. We'll keep our ear to the ground, shall we?
Absolutely.
Well, thank you so much for this walkthrough. This has really made some of those concepts about not just RF basics and helping our audience understand what goes into radar design, but also giving that context of the how and the why, I think really is powerful. So thank you so much for walking us through that.
You're very welcome. I enjoyed it.